Welcome back, everybody. In this video, we're continuing to look at section 4.1 with more examples. In this example, we're going to be looking at a situation where we have a percentage decrease per year instead of a percentage increase. So we developed the compound interest formula with the idea that a certain amount of money could increase by calculating interest on top of interest. In this example, we're going to see a percentage decrease. So we could go through a similar sort of derivation for this, and it's going to be really close to what we would have had for growth. If it was going to increase by R percent per time unit, let's go with T for T years, then it would be 1 plus R. So we had 1.10 for a 10% increase. Since this example, we have a population of 6,000 decreasing by 3% each year, it's going to be a decrease. So it'll be a subtraction of 3% every year. So the formulation looks like this. We have an initial population of 6,000, and we'll have 1 minus 0.03 to represent a decrease of 3% each year. And that will take place after 10 years. And that will be the future amount. Okay, so let me calculate that. So inside of the parentheses, 1 minus 0.03 is 0.97. So we'll get 4,425. All right, so that is how the decrease formulation looks. In general, here's the formulation for a decrease. If you have N0 as your initial amount, whatever that is, then N is the amount you will end up with after T time periods, and the decrease is by R percent for every time unit. Okay. With different types of compounding, daily, monthly, weekly, quarterly, or annually, it can be hard to compare and determine which of several competing investments or loans might be best. And so for that reason, we have something called the annual percentage yield, which helps. And so what the annual percentage yield is this, is the equivalent simple interest rate that it would take to give the same result as a given compound interest. An example is going to make that clearer. Okay, suppose that an investment earns 4% annual interest compounded quarterly. We'd like to find the annual percentage yield. So let's do that. And how you do that is basically we're going to figure out the future value of $1, just because $1 is easy to work with. And we'll see what that would grow to using this scheme. So $1 at 4% interest, compounded quarterly, that's 4 times a year, for 1 year. So 4 compounding periods and 1 year. So let's see what that amounts to. Okay, so we're going to calculate that. That's 1.01 raised to the 4th power. So it's all right, so that's about 1.04060401, or let's just say 0.0406. Just forget the rest of it. So so basically $1 using 4% annual interest compounded quarterly would grow to 1.04 and then fractions of a penny. So the annual percentage yield here would be 4.06%. So what that means, what does the percentage mean, is here we know that compound interest will pay you more than just using simple interest. So the question then is, what would be the simple interest you would need to match the effects of compounding? And so that's what annual percentage yield tells you. is if somebody offered you 4.06% simple interest, that would be the equivalent to the 4% annual interest compounded quarterly. Okay, if the compounding is done daily, we'll see that we need to have a higher equivalent interest rate. So if the compounding is daily, it'll be $1. We're still doing 4%, but it's compounded daily, so that's 365 times a year, and 365 times because we're doing it just for 1 year. And so let's see what we get. Okay, so that's about 1.0408. Okay, or 4.08% interest. Okay, so the usefulness of the annual percentage yield is that it helps you be able to compare a couple of different competing investments or loans, because if they're compounded two different ways, then you could calculate their APY, and then if you're looking at an investment, whichever is higher is better. Okay, so here's an example. Suppose that Realty Income Corporation has an investment with a 3.91% yield, and it pays a dividend monthly. Store Capital has a yield of 4.1%, but pays quarterly. So we want to know which one is higher yielding. So the thing is, Realty Income has a lower percent. It's 3.91 versus 4.1%, but it pays monthly. Store Capital has a higher interest rate, but doesn't pay as often. So it can be hard to decide, well, which one of these would be better. So what we're going to do is calculate the annual percentage yield for both. So let's start with Realty Income Corporation. So there we could take the future value of $1. So $1 at 0.0391, and it's monthly, right? So that's 12 times a year, 12 times for 1 year. And let's see what we get. Okay, that's about 1.03981. Okay, so that would be like about 3.98% APY. And then Store Capital, that's going to be 1 plus 0.041. Let's try that again. But that is paying quarterly. So that is 4 times a year. All right, so going through the calculations, we can see that Store Capital would have a APY of 4.16%. So in spite of the fact that Realty Income pays more often, monthly versus quarterly, the fact that Store Capital's interest rate is higher at 4.1% than the 3.91% that Realty Income pays, Store Capital still would be the better investment of the two, even though Realty Income pays interest more often. Okay, more examples. So for this one is about a mouse population. So here it says a certain breed of mouse is introduced onto a small island with an initial population of 320 mice. And scientists estimate that the mouse population is doubling every year. We want to find a function n that is modeling the number of mice after 2 years. We want to estimate the mouse population after 8 years. So the initial population is 320 mice. So that means that at time 0, we should expect 320 mice. And then I just multiplied by 2 to start creating this table. Each year that goes by, we're going to multiply through by 2. So then our function that would give the population after t years, we'll say n of t, the number after time t, will be n0, which is our 320 mice initially. And then we're multiplying by 2 repeatedly. And we're going to multiply by 2 raised to the t power. Double check that that would fit with the table that we have below here. When t is 0, we'd have 2 to the 0, which is just 1, so that would give us 320, and so forth. So double check to ensure that that would be the correct formula. And then once we've done the formula, then it's a matter of substituting in 8 for our t. So we'll have 320 times 2 to the 8th power. Okay, and that's 81,920. Of course, that's a simplified model, assuming that there's no predators or anything like that, but that's how the math works out. One interesting change that we can make to this is to say, okay, well, what if instead of doubling every year, what if it doubled every 3 years? How would that go? So to think about that, we'll again start producing a table. So t and then n of t. So we initially have 320. And then I know that I don't know how many there will be after year 1 or after year 2, but I know after year 3, that's when it's going to double to be 640. And then after 3 more years, then it's going to be up to 1,280. I don't have a way of figuring out right now exactly how much there will be on the kind of in-between years, but I know that every time I hit a multiple of 3, we're going to be multiplying by 2. So how that's going to affect our formula looks like this. We'll have n of t, and we'll still start with 320, and we'll have 2 still raised to a power. But I'm not going to have 2 to the t power anymore because we're not multiplying by 2 every time t goes up by 1. We're multiplying by 2 every time t goes up by 3. So we'll have t over 3 in our exponent. So try it out. When t is 0, our exponent is 0. So we'd be multiplying just by 1. 320 times 1 is 320. When t is 3, 3 divided by 3 is 1. And so we'll have 2 for our multiplier on the 320. So that would be our formula. So after 8 years, do you think there will be more or less? Well, if they're doubling every 3 years instead of every year, it should be less. Okay, so let's see what we get. All right, so 2031. 2032, I guess I rounded up. Okay, so just a couple of examples. This one about growth of populations. Okay, we have 2 more. Okay, and then we'll be finished with this, okay? All right, so now the story for this one is from our textbook. The story is that a scientist starts off with 100 milligrams of a radioactive substance that decays exponentially. After 35 hours, we know that 50 milligrams of the substance remains. After 54 hours, we want to know how much there will be. So for this, we need to decide on a model that's going to be appropriate for this. For this one, we're not given like a percentage decrease or increase. It just says it decays exponentially. So I'm going to use the natural exponential model for this. So we'll have, we'll call it n of t. So the amount that we have after time t. That will be n0. And then we'll have e raised to the rt power. And we're going to see that the value for r is going to be negative because this represents exponential decay. So we need to figure out the value for r first. So we're going to start by substituting in the values that we have. We know that we start off with 100 milligrams. And so that will represent our n0. And after 35 hours, half of it's there. So E raised to the R times 35 hours, we only have half of it left, so 50 milligrams. Okay, so for here we have to start thinking about how to solve for our R. So let's do that. All right, so taking a look at the way that I've started this, it's become apparent that if we're going to continue this way, I need to be able to find the value of R that is in the exponent. And so far, we haven't done enough work to enable us to do that. We would need to learn about logarithms in order to get it done that way. So rather than take that approach, we're going to try a different way instead. So the other kind of formulation that we'd had for exponential functions, our first one that we started off with, was f of x is a b to the x power. And so for this, our initial value was a, and so that for this problem is going to be the 100 milligrams. And then we're going to start substituting in some of the things that we know and see what progress we can make. So we know that after 35 hours, there's 50 milligrams of the substance remaining. So f of 35 hours is equal to 100 times b raised to the 35th power. And that's going to be 50 milligrams of the substance remaining. Okay, so from here, we want to see about solving for B. What's different about here is that the unknown is in the base. The way that I had tried to set this up before, the R, my unknown was in the exponent. We don't have tools to enable us to get that done yet. So instead, we have 100 is times B raised to the 35 power is equal to 50. So we'll divide through by 100. B raised to the 35 power is 50 over 100, or 0.5. And so we have b raised to the 35th power is equal to 0.5. So then in order to get that b alone, we're going to need to basically take the 35th root of both sides. So I'll take the b to the 35th power and raise it to 1 over 35. And then we'll also take the right side, the 0.5, and raise it to the 1 over 35 power. Okay, so then on the left side, we have using the power to a power rule for exponents. A raised to the m raised to the n power is a raised to the m times n power. 35 times 1/35 is 1, so this will give us b to the first power, and that's 0.5 raised to the 1/35th power. And so that's something that we can calculate. Be very careful as you type this into your calculator, use exponents as needed. So here I'm getting about 0.9804. Okay, for our value for b. So then going back to the original question, we want to know how many milligrams will remain after 54 hours. So our goal here really is to build the function that we need so that we can then evaluate it after the 54 hours. So our function looks like f of x equals 100, that was our initial amount, times 0.9804 to the x power, and we're going to evaluate that for 54 hours. Okay, so let's go ahead and calculate that. Okay, and that's about 34.3. And that will be milligrams of whatever it is. Okay, all right, so that will do it for section 4.1 and this video. Let me know if you have any questions, and have a great day.